I was mentioning the other day that sometimes we don't find bus 1 as the swing bus or the reference or the slack bus. It can be a different bus depending on where the highest generation facility P and Q are located. Now the admittances between the buses, meaning the interconnecting lines, are given Z12, Z23 and Z13, and there are other P and Qs. You can see for bus 1 is P1 plus JQ1, for bus 3 is P3 plus JQ3, and their values are also given. P1 plus JQ1 is 0.45 plus J0.25 as the Q2, and then for the load on the bus 3 is P3 plus JQ3, which is minus 0.8 minus J0.35 per unit. And then on the bus 3 there is a shunt capacitor connected. So that's what the difference is as compared to the other examples. So in this case, what we are asked to do, we are asked to find out the voltages at the bus 1 and bus 3, and then we also we need to find out the power at the swing bus, meaning at the bus number 2, and also mention whether the power is lagging or leading or what is happening there in terms of the lagging reading of the swing bus. So the shunt capacitor power rating is given here. So what we need to do first, we need to know the admittances. So is that clear with the problem, or do I need to explain it more? There is a 3-bus system. Just let me repeat it. It's a 3-bus system: bus 1, bus 2 and bus 3. So bus 1 has some PQ, bus 3 has also PQ, bus 2 is a swing bus, and the interconnection impedances are given: Z12, Z13, Z23, and on top of that there is a shunt capacitor connected to bus number 3. We have to find out the V1 and V3 after one iteration. I always kept it one iteration to make it simple for our hand calculation because we're not using computer. So after finding out the V1 and V3, we also have to find out the power at the swing bus, which is bus number 2, and whether the power factor is leading or lagging, we have to determine that. And the rating of the shunt capacitor is given as 0.18 per unit. So we need to now go and solve this problem. So let me just add a new slide. First of all, we need to find out the admittances. So the admittances, for just to make it generalized for you, we need to know the Y10, Y small y's. These are small y's, small Y20. Goodness, this capitalized things: Y20 and Y30, meaning those shunt capacitances from each bus to ground. 0 means 30 means between the bus 3 and ground. So for bus 1 and 2 there is nothing, so they will be 0 straight away. And for bus 3 there is something, the shunt capacitance is there, so it will be equal to 1 over Z30 because its admittance we can find out it from the impedance, and impedance is calculated from the shunt capacitance value. So it will be 1 over negative of the shunt capacitance XC, 1 over minus JXC because it's capacitance. So if we simplify that 1 over minus JXC, what we will get? we'll get it will become J over XC. And we also know, I'll come to this line up there, we know this formula, XC is V squared over Q. We know this is a general expression, XC is equal to V squared over Q. This one we know. And if we go up there now, replace that one, we can now find out what will happen. Some are waiting in the lobby. So J is there, and X is equal to V square over Q2. V is what? V is the corresponding voltage of bus 3. So if we go back up there in the formula, what is V? V is this 0.98 at an angle 0 degree. So that's the voltage of bus 3. So that's what we need to use. So 0.98 V squared. So squared over the XC, which is 0.18. Put another J over another bracket there. It will make easy for us to understand. Can you see what I have done so far? Because the shunt capacitance is there, now I did not need to write the Y10, Y20, Y30, but I wrote it in case in another problem you might have a shunt capacitance between the bus and the ground present. But in this case there is none, so I just kept them to be 0. It will make us understand that if we have some shunt capacitances, we have to consider for all of them. So we wrote the expressions for Y10, small y, if you have to remember that, small y10, small y20, small y30. Looking at the system diagram, what we find is that there is none onto bus 1, bus 2. So Y10, Y20, they are zeros. And then we come to Y30. Y30 is equal to 1 over Z30, reciprocal of the impedance. And that impedance is minus JXC. So I replace that by minus JXC. And after that, we just simplify. Then we get J over XC. And XC is what? XC is V squared over Q. And the power rating Q is given, the reactive power, because this capacitance is not P. You have to remember that is Q. Q is the power rating that is mentioned in the problem because it is capacitance. So we are assuming that it's a pure capacitance. There is no resistance. If there was resistance, some P will be present. So V squared, V is the respective voltage of bus 3 because we are calculating Y30. So we need to take the voltage of bus 3. We go back to the problem and we find that the voltage of bus 3 was given as 0.98 at an angle 0 degree. So 0.98 squared over 0.18, which was the power rating. Can you tell me this value? Who has calculated it? Who has calculated this value for Y30? .187, that's correct. Anyone else? J 0.187 per unit. Anyone else who can confirm this value is correct? You are getting the correct value. Umishan says yes, that's good. So we have the value for y30. Now we can go and calculate other admittances. So in this case we need to calculate the other admittances. Let's go and calculate them. So let's calculate y11 that we will need. Y11 will need, so y11 is what? All the admittances that are coming there. So we calculate y10, which is 0, it's not there, y12 and y13. So you can calculate it now and tell me the final value of y11. Anyone who has the value of y11? Okay, Sibu Siso also confirmed that it's the same value. Now you calculate y11 and tell me y11. You can put those values straight away from the diagram. y12 is 1 over z12. So it's 0 plus 1 over z12 plus 1 over z13. So what we get? We get minus j15. That's the correct answer. Can you please confirm? Anyone else? Sahil and Subusi, so they are saying j15. So minus j15. So that's correct. Now we can calculate y22. Y22 is what? Y20 plus y21. There is connection between 2 and 1. So 2 and 1 will come. And also there is connection between 2 and 3. Okay, let me just put this diagram here so that you can see it. Two one and also y23. Now we'll do the same thing. Y20 is 0 and then y21 is 1 over z21 plus 1 over z23. What's the final answer for this one? J3.33. Is that correct? Can you check it? It will be equal to 0 plus 1 over j.1. 1, 2 is 0.1 and then plus, yes, minus 16.667. That's like a j.1 plus 1 over j.15 will give you minus j 16.667 per unit. You must always write the unit along the answer that you got all the time. So we can now come to y33. So y30 plus y31 is there. So y31 plus y32. So for this we have y30 value that we have calculated. So that was j.187 plus 1 over j.2 plus 1 over j.15. So that's y33. Sahil, did you get the answer correct, 16.77, or you still with j3.33?
So I get minus 16.67.
Thank you. So you can now go for y33. Sibusis also has the same. So we have three people saying these things. So that's correct. Now we got the admittances of y11, y22, 33. Did you notice that I did not calculate the others here? Because we did not ask, that the problem did not ask us to find out the bus admittance matrix. But if you practice it, you will know. If that is not asked in the tutorial, you don't need to calculate all of them in the first place. But you know, you will know which admittances you will need in the following steps to calculate the voltages and so on. So you can just calculate those to save time and effort. So we have to calculate the V1 and V3. So let's go to that equation. So V1 equation will be how we can use that. Let me just go up and copy those equations from here, Vi and this one, so you can utilize them to calculate V2 is shown, for example here V2 is not required for this one, so you can calculate V1. You can write down the equation putting I is equal to 1 and K will change from 1 to N. N is 3 here and I cannot be equal to K. So what will be the equation of V1? We don't need this V2. Let me just remove it, otherwise you will get confused. What will be the equation of V1? V1 will be equal to 1 over y11. Let me just copy this and then paste it here. Too small. Yeah. So if we expand this equation for I is equal to 1, so we'll get V1 is equal to y 11, then it will be V1 minus JQ1 over V1 conjugate, and then this thing needs to be now expanded. So when we expand it, what we get y12. I cannot be equal to K, so 11 y11 will not be there, and then V2. So like this, and then plus, I'm using bracket, or you can remove this bracket straight away. You can use minus here, minus y 1 3 e3. So e3, is that clear? So if you use all the values of the voltages and powers, you should be able to now find out the value of V1. Can you do that and let me know? Anyone who has answer for this one?
I'm still working on it, sir.
Oh no, that's perfect. Okay, now if we have the V1, we can go to V2, sorry, V3. So if we replace the equation here, so it will be equal to V3, and then we go and change the others. V3, this one will be P3 minus JQ3, V3 conjugate, and then we will have to look for if I is equal to K or not. So 3 1, I is equal to 3 here. Oh, sorry. I is equal to YIK. So 3 1 IK, K is 1. So V1, let me put it, sorry, control. V1, let me keep it like this. Control is V1, Y31, V1, and then 32 can be there. I is not equal to K for 32, so that's fine. So K is equal to 2, so we can put that 2, and then we go for 33, Y33, it won't be there because I will become equal to K, so we can now say that it's complete. So what should be the value of this? V3. 1.066 promotion 1.066. Anyone else? Okay, he's saying you made a mistake. I have 0.99.
Sorry, sir.
Mm,
For the Y31,
mm.
is it negative 1 over Z13?
Y31, we calculating capital Y31. Listen, everyone. Thank you for asking that. We putting in this equation we have capital Y31. So before we do that, capital Y31 is negative of small y31, and now you can make it easy. Small y31 is what? Negative sign remains there, and then small y31 is 1 over z31. So it will become j5 finally. Capital Y31 will be equal to J5. And also make sure now V1 is the V1 that you calculated in the previous case, meaning that 1.009, because it's you have the updated value of V1 and at an angle of 1.65.
Okay, so I think I understand now.
Yeah. So everyone can calculate these values, right? We can go to the next step. Next step is to calculate the power at the swing bars. Next step is to calculate the power at the swing bars. So let me just put it a little bit on this side. Okay, let me keep it inside here. So the next one is the power at the swing bars, which is bus number 2, and power is what? We know that is P plus JQ, but you using V conjugate, so it will be P minus JQ. So P2 minus JQ2. So P2 minus JQ2, how do we calculate it? V2 conjugate I2, V2, I'm writing it in bracket, because putting the superscript and subscript in this PowerPoint is challenging. So V2 conjugate times I2. V2 conjugate times I2, and V2 is what? We calculated that value. Sorry, the V2 is there in the problem in the first place. It was given, V2 was given 1 at an angle 0 degree per unit. Is given here. V2 was given here. So V2 is there. So 1 at an angle 0 degree, 1.0. You don't need to put 0 degree, and then it's multiplied by that expansion. I2 is equal to Y22 times V2 plus Y. We can start with actually Y21. I don't know why I wrote Y21 V1, Y22 V2 plus Y23 V3, Y21 V1, 22 V2, Y23 V3. So if we put all those values, we will get the answer that I will wait for you.
Sorry, sir. What is your value for V3?
Value for V3. My V3, let me check. It will be a little different from yours because of approximation, but my value was, let me write it in terms of A plus JB. It was 0.98, 0.9, where is 0.9884 minus J 0.575. 9 is missing. That's the V3 that you will need here. All the values that are updated, meaning V1 and V3, V2 is coming from there. The updated values of V1 and V3 will be used, and V2 is 1 at an angle 0 degree given in the problem because it's a swing bus.
I'm sorry, sir.
Yeah.
For the phase angles, for the voltages, are they generally close, like very close to zero, or can you get like large phase angles?
No, normally it's small, but it won't be zero in most of the cases. If the load is too abnormal, meaning too much of unbalance is there, then the phase angle will change much.
Also, sir, for the power at the swing bus, we're using the updated values for V1 and V3.
V1 and V3, that's what I mentioned. V1 and V3, we will use the magnitudes and angles that we are getting from this equation and this equation, and V2 is coming from there. Always updated value.
Okay, sir. Sorry, sir, could you also zoom in as well? Could you also zoom into that slide a bit more? The resolution on my screen is not so good.
How I can?
Yeah, that's fine, sir. Thank you.
I can make it a little larger. I reduced the font size for those two equations, V1 and V3, just wanted to accommodate everything in this slide. It's not 0.5, it's 0.05.
Okay, so I actually got that value for V3.
Which one? 0.5?
Yeah, 0.5. That's what I was asking about the phase angle.
Yeah, that's what phase angle you got?
Like -3 or something.
-3. Okay. I'm writing that just as an approximated value.
Yeah, I can't remember it exactly because I exited.
No, that's okay. We can always double check, and we have to practice it at home for everyone. So when you have the power at the swing bus, you will let me know. In terms of this will come as P2 minus JQ2. Size is 0.28 J643, but what I got, let me help you. What I got is 0.0653 minus J 0.0153, something like that. So you will get something similar to that. The exact value will differ because of your approximation and my approximation in terms of calculation. So that's P2 minus JQ2. So to know the power that we have calculated now, the answer is okay, but not immediately. So what we have to do, we need to convert it to P2 plus JQ2 form. That's our conventional form. P2 plus JQ2. So what we'll do, we'll change this side plus as well. So when we have this, we see the sign of reactive power is positive. Therefore, swing bus is lagging, which is the normal case. So that's what you have to notice or observe here, that you need to now go back to P2 plus JQ2, which is a conventional form, changing the sign, and then look at the sign of Q2, which is positive here, and as it is positive, it's supplying the active power, so it's lagging. That's that one. Can you please take note of this quickly? I want to go to those questions that were asked to answer, but before that, maybe I will take a 3 minutes break for you, because we did not stop in between. Is everyone okay with this answer? Can you take note of this, what is written there on the screen? For the calculation of power at the swing bus, P2 minus JQ2 by V2 conjugate I2, and then we get the answer in terms of P plus JQ, meaning P2 plus JQ2. We change the sign of Q because we're changing the sign of Q2 from the original equation that you used, P2 minus JQ2. So P2 plus JQ2, change the sign on the right hand side of the equation for Q2, and then we look at the sign, it's positive, therefore it's supplying the active power and it's lagging. If it was negative, then it would have been consuming the active power from the system, that 3-bus system. And power factor will be leading in that case. Is that okay with everyone?
Yes, sir.
Okay, so can I now go to answer the questions? There are quite a few questions that were asked. I wanted to take the opportunity to explain them in the class. I have them in my slide. So now it's 11:33. Let me take 2 minutes to give you just a break. I'll start at 11:35.
I'm sorry, sir.
Yeah.
For the power at the swing bus 2, the V2 is 1 per unit, am I correct?
V2 is 1 at an angle 0 degrees.
Okay, thank you.
For that question, thank you for asking again for everyone. As V2 is related to the bus 2 and bus 2 is predefined as swing bus, normally we ask or calculate the voltages at other buses, not the swing bus. So that's why it's still the same value that was given in the problem in the first place. So it still remains 1 at an angle 0 degrees. We did not, because for swing bus we want to know after the load flow study what are the p values and q values they are going to supply. So this is also, this example is also showing that these are the p values and q values that needs to be supplied by the swing bus so that the system remains in steady state. Although I did not ask or did not write the question in that way. So to determine the power that needs to be supplied by the swing bus, at least at the first iteration level, is this. It will change if you do more iteration. To change, if you do more iteration, you will get new values of v1 and v3. As you would get new values of v1 and v3, you will get different values for p2 and q2. Okay, can we go to the question now? It's 36. So you see the first question is like this. Why is it that in South Africa the power frequency 50 Hz, whereas in other countries it may be more? Yeah, it's a choice what frequency is going to be the power system's frequency or mains frequency. We call it sometimes line frequency. It depends on the choice. So it started at the very beginning when electricity came into the scenario and power generation facilities were being installed and started operating. So they choose. Normally we have two different frequencies across the whole world, which is 50 Hz and 60 Hz. So the countries normally choose, and according to that choice, many things will happen later on. So they chose it to be 50 Hz, like India also has 50 Hz, and many other countries has 50 Hz. And whereas in other countries it may be more, it's not like maybe more, it's maybe more, but not many different frequencies higher than 50 Hz. I have had a list of countries at which frequency they are operating, but for now I just have shown on this table the countries that are using power system frequency as 60 Hz. All others are using 50 Hz. So these are the countries, as you can see, America, Samoa, Anguilla, Antigua, West Indies, all those West Indian small countries that like Puerto Rico, then Trinidad, Tobago, Virgin Islands, small island, British Island, Brazil, big countries like United States, where the United States name is here. United States, one of the biggest country, 60 Hz. And then Canada should also be there. Where is Canada? It's also 60 Hz. But if you go to Asia, you might find that there are some countries like Japan, they're using 50 and 60 both. These country Guyana, they are changing. They are still at the moment they have both 50 and 60, but they're converting 50 hertz to 60 hertz system. If you go to North Korea, they have both 50 and 60 hertz as well. So they choose actually, and according to their choice, then the country operates at that particular frequency. Now, when they make the choice, is the engineers and then also from where they're buying the generators, turbines, and things like that. So if I go to UK, Newcastle upon Tyne, and if I order my turbine generator set to them, they will normally give me 50 Hz because that's what they're producing. But they also can make it 60 Hz if I want to make my system 60 Hz. So we choose actually at what frequency we are going to operate. But again, there are a mix at the moment. Some countries are operating at 50, some countries are operating either at 60, some countries are operating at both 50 and 60 Hz. And the choice is on the policy makers or the people who are on the implementation side and decision making side and things like that. So South Africa has 50 Hz, India also has 50 Hz. And if you go to United States, then you will find 60 Hz. If you go to Canada, you find 60 Hz, big ones. And if you go to Japan, you go and get both 50 and 60. Now, how they operate, both they are different. how they interconnect? You can interconnect two systems which are operating at two different frequencies, 50 Hz and 60 Hz. You use convert the 50 Hz system to 60 Hz by a converting station. We call them converting. So like we use transformer to convert a voltage level to either higher level or lower level, stepping up or stepping down. The same thing we can do here when we have a converter. So we can step up the frequency to 60 Hz or step down the 60 Hz frequency to 50 Hz so that they can interconnect and they can also participate in the integrated grid. So that's that part. Why is it frequency? Why is it 50 Hz in South Africa? It's the choice. And then if I come to the second question, is that answer clear or was it too short?
No, sir, that's fine.
Okay. So now the next question, how does the wind power manage to keep the frequency? It's the same thing that I was describing for the thermal power generators, that when the frequency changes, it goes to the rotor. Either rotor will start spinning at the higher speed because N is equal to 120 F over P, or it will start spinning at lower speed depending on the frequency if the load demand is too much. So that energy, excess energy or short of energy will be reflected on the generator rotor. But say it's mainly, if you go back a little bit, it's because it's happening on the inertia of the system, meaning the turbine, generator, rotor, which actually participate in that inertial process. So actually the inertia responds immediately when we connect electrical load to the generator or we draw some load from the generator. So if you connect some more load on the generator, the inertia will respond immediately. So it will drop its speed, giving the energy from its own because of that kinetic energy that it has because of rotation. A similar thing happens if you withdraw some load, so meaning the energy is not being consumed now, so that excess energy from the load side will be reflected on the generator rotor. The same thing happens in wind turbine as well. Inertial effect is there. That's the first part, mechanical. We don't have to do much, but we need to control that part. So for controlling, what is done, we put electronic converters, like in thermal power plant or hydroelectric power plant we put, or also in gas turbine power plant we put a governor that responds to that frequency to control the input mechanical power to the system through water or through steam or through the gas input to the gas turbine. So in wind turbine we cannot control the wind. That's the problem as compared to those other examples that I gave for thermal steam turbine or water turbine or gas turbine. We can control the input water, we can control the input steam, we can control the input gas to the gas turbine. But for wind turbine, we cannot control. So what we do, we use electronic converter, and those electronic converters at the back end of the converter, there are many different types of control algorithms that are being researched and implemented in industry, and they put them in the operation. But for example, one type of generator that we used for wind turbine generation is called doubly fed induction generator. Doubly fed means it's a generator that is connected, the stator is connected obviously to the grid, also the rotor is connected to the grid, whereas the other generators like our synchronous generators in thermal power plant, only the stator is connected to the grid. The rotor side is controlled by the power plant operators or the generator operator to control the excitation, to control the reactive power and the generator terminal voltage. But for doubly fed induction generator in wind generation, we have the rotor connected to the grid as well, but in between the rotor and the grid there is a converter. So by controlling that converter, we also control the frequency. So inertial effect and electronic converter controls the frequency of power generation in wind turbine cases. But if we don't use doubly fed induction generator, if we are using only simple induction generator, the stator is connected, but we still have electronic converter to control the frequency. If we use permanent magnet synchronous generator for interference generation, then we also have a frequency controller, electronic controller. So those different types of algorithms and controller you can just imagine what type of controller. It can be PI controller or PID controller, but normally we also consider the other aspect that we have in our control system that we study, like should it be a critically damped system or over damped system or under damped system, what type. So we need to make sure whatever algorithm we are using, on top of that we need to consider that part. If we are going to use over damped system, under damped system, or critically damped system, looking at the settling time, looking at the steady state error, and all those aspects are embedded in the system. We cannot just ignore them. But in general, an electronic converter or controller is there that is used to control the frequency for interval generation. But if we want to look at those things, it's a huge area of research. One can just spend whole life onto that part and must not or cannot possibly finish the task, but can obviously learn a lot. So is that okay with question number 2? Everyone, if any one of you has some question, you can ask for question number 2. I'll come back to question number 1 again. Is that okay with question number 2?
Yes, I think so. That's fine.
Thank you very much. The third question was very interesting. What is power mismatch and what is the unit of measurement for power mismatch? So power mismatch is something that comes especially very relevant with this load flow study. So if you imagine that we have buses in our power system and we generalize them using the letter I, small I, so ith bus. So if we consider ith bus, so let's consider that ith bus has generation, meaning it is supplying PGI, active power, and QGI, reactive power. So that's the generation of that ith bus, PGI and QGI. Now we also can think that on that same bus some loads are connected, meaning it will have active power consumption, reactive power consumption. So we can call them PLI, meaning load of ith bus, PLI and QLI, right? So what is happening now, active power injection is considered. Active power injection is considered for that particular ith bus. So we have PGI, we have PLI. So what is active power injection? Is the difference of these two, meaning PGI minus PLI. Similarly, we can go for reactive power injection. Reactive power injection will be QGI minus QLI, right? Now, when we have this active power injection and reactive power injection being the difference of respective active powers and reactive powers on that ith bus, we now know what is P injected and what is Q injected on that ith bus. PGI minus PLI, Q injected is QGI minus QLI. So that's injected. Now when we do load flow study, we will calculate P and Q. Now when we calculate the P and Q, we have now another P value. So now the difference between P injected and P calculated is actually the power mismatch. The difference between Q injected and Q calculated is the mismatch. So you do one iteration, you get one mismatch. You go to the next iteration, you get another mismatch. You go to the next iteration, you get another mismatch. So in power flow study, what we do, we consider this mismatch, and the unit of mismatch is respective unit. If we are considering active power P, the unit will be watt or kilowatt or megawatt or gigawatt. Similarly, if we are considering the reactive power consumption, and the mismatch will be the difference between Q injected and Q calculated, and the unit will be reactive power, var or kilovar or megavar. Now our task or our aim in load flow study is to make sure that the mismatch is zero. So that's why we do a lot of iterations in the first place, so that that mismatch is not there, meaning the P injected is going out as we calculated the value, meaning the P injected and the calculated value should be equal, meaning the mismatch should be equal to zero. That's what we aim. And this mismatch, like I mentioned, it can be P, it can be Q, it can be apparent power, MVA or kVA or volt ampere if it is small system. So the unit will be respective, megawatt, megavar, MVA. You can also find out mismatch in MVA capacity. Is that clear? Or do I need to say something more? If you have more question on this, you can ask.
So sir, it's like an error between what's calculated and what's actually happening in the system.
Yes. What is being injected and what is being calculated, and the calculated value changes
With each iteration.
with each iteration. Like this one, you saw that a P plus JQ to we calculated this value, right? So if we go for another iteration of V1 and V3, this is the iteration number 1 only. We did not do second iteration. If we do second iteration for V1 and then we'll do second iteration for V3, and then we'll have updated values here for V1 and V3, then we'll get P2 and Q2 different from this 053 and 0153, meaning this is the calculated value. But the injected value is coming from the generator itself onto this swing bus. So there will be a mismatch, and each and every iteration will generate a different mismatch. And our aim is to get that value as minimum as possible, possibly zero.
So sir, that injected value is measured.
Yes, that's measured.
Okay,
that each and every generator is supplying, because that's real value. And these are intermediate values. These calculated values are intermediate values. And when you are done with power flow, you will control, or the operator will control the generators connected to the swing bus, so that that calculated value is now reflecting back to the generator P and Q values. It's not clear. Let's say I have a swing bus where I have 50 megawatt and 40 megawatt connected. The generator supplying 50 megawatt and 40 megawatt, and it doesn't matter how much loads all those things are connected. Now I'm starting doing the load flow study, and then I find that my P is, after first iteration, it's 45 megawatt and 32 megawatt. So it's not making any close approximation with the 50 megawatt and 32. So I do other correction, and if I find that it's still saying after 10 iteration or 20 iteration, it's still saying 45 and 32, now my control at the generators of the swing bus to change that megawatt to 45 from 50 and megawatt from 40 to 32, because that's the mismatch.
Okay, I understand, sir. Thank you.
And when we control the generators such that megawatt now becomes 45 and megawatt becomes 32, the mismatch is now zero, so that the system is steady.
So they control the generator to the values we calculated, like they try and match those two.
Yes. But again, this will be reflected, this difference will be reflected in terms of the frequency, in terms of the voltages. That's why we look at the voltage. The reactive power will be reflected on the voltage, active power will be reflected on the frequency. They are two different. When we want to control the reactive power, meaning I have a generator now operating at 32 megawatt, supplying 32 megawatt. I want to raise this reactive power, or why I want to raise this reactive power to 40 megawatt. The reason is that I see the generator bus voltage is not at the rated value, is below the rated value. So let's say the generator voltage is 0.98 per unit. I need to be at 1.0 per unit. So for that to happen, I need to excite the generator more so that it reaches the terminal voltage at its rated value of 1.0 per unit. As I try to excite the generator more by controlling the exciter current, DC current, it will draw more current, the magnetic flux will be more, and it will in turn give us more voltage at the generator stator terminal. Because of that increase in voltage, the reactive power now will increase and possibly like will go to 40 megawatt. If I want it to be 40 megawatt, I can do that by controlling. But again, we'll also have to consider other things, like when I'm saying I'm increasing the excitation current of the rotor field winding, I need to know that the maximum rotor field current that rotor can carry, I don't want to damage that one. When I want to increase the rotor excitation current, it reflects to the reactive power and the generator terminal voltage. I want to be at 1 per unit, but the reactive power is also increased. Because of increasing reactive power, the generator stator current will also increase. Then again, I will also need to know what is the maximum stator current allowed for this generator. So there is a limit for that one as well. As you increase the reactive power, keeping the active power, we're not talking about active power at the moment, we're only talking about reactive power. As you increase the reactive power, the MVA rating, MVA power supply needs to be compared with the MVA rating of the generator. So that is another part. Right, so all those things will come into the scenario. Again, it will come to the scenario of power factor. When you keep your P constant and increase or decrease your Q value, it will also change the power factor. It will become more lagging. If you keep your P constant and increase the Q value, the power factor will start decreasing, and how far you go, that you will decide. Now if you are at 0.9 power factor lagging, you can go to 0.88, 0.87, 0.85, it's okay. But if you are operating at 0.8 and still you want to go to the rated value of voltage 1.0 per unit by increasing the excitation, that will increase the reactive power, but that will drop the power factor, which you cannot possibly afford. So in that case, you will have to do something else. What you can do, you can use a capacitor bank on the load side to boost the reactive power and the voltage of the buses, meaning you have reached the limit of your generator control. So there are limits, all those stator winding current, MVA capacity, the reactive power capacity, power factor, stator current capacity, rotor current capacity, and all those you consider. It's not only one parameter, one is related to the other, and they are always reflected in either from each other. You will see the effect of each other everywhere. So if you limit if you reach the limit of the generator controls, exciter control, then you have to go for shunt capacitance connected in the system that will supply some reactive power and boost the voltage of the buses. Is that clear?
Yes, sir. Thank you.
Okay, so now I want to come back to the question number 1. Okay, I think it's 11:15 and I have a meeting at 12 today. I should join that one. I will still have to say something here on that question number 1, which is embedded inside the question that you asked, but I did not mention that part. I wanted to come back to that one. I'll come back on next week. Is that okay?
Yes, sir. No problem.
Yeah, I will remind me.
I'll do that, sir.
Yeah, thank you very much. Keep well, and yeah, we'll talk next week then.